Hello student, welcome back to your physics teacher, and in this we're looking at section 11.6 from the Nelson textbook. I'm going to go over the questions from the homework, that way you get a better understanding, so make sure that you stay tuned. And we're going to be looking at Kirchhoff's laws, so the Kirchhoff current law and the Kirchhoff voltage law. Written as KCL and KVL. So once again, we're looking at Kirchhoff's laws. So the first question here, it asks us, what is wrong with the following information? State whether you're applying KCL or KVL in your answer. So as mentioned, KCL is Kirchhoff's current law and KVL is Kirchhoff's voltage law. So the first one is A. The current going into a parallel circuit is listed as 0.5 amps, and the current coming out of the parallel circuit is listed as 0.3 amps. So again, with this question, each of these statements there's something wrong, so we need to try to correct it. So in the first one, the current going in is 0.5 amps. And it is going into a parallel circuit. And then they measure the current coming out. So we use the letter I for current, so current in and then current out. But this student measures 0.3 amps. So this would be a violation of Kirchhoff's current law, because all the current going to a junction will be equal to all the current out of that junction. In other words, the current in should be equal to the current out. So we need to make this correction, and this should have read 0.5 amps. So the correction is all the current going into a circuit junction will be all the current equals to the junction at the output. So and this was by the Kirchhoff's current law. Part B, a student measures the voltage across each of the three loads in a series circuit to be 10 volts each. The voltage across the source is measured to be 10 volts. So we have a circuit connected in series, and there are three loads. And across each of these loads, each of them are 10 volts. And then they measure the voltage across the source. So the source could be like a battery. So V source, 10 volts. Now in a complete circuit, all the voltage from the source needs to be lost in the circuit. So this will make sense because the source is 10 volts, and if the first voltage drop is 10 volts, then there will be nothing left over for the other two loads. So this is a violation right away. So the only way this would be true is if the source, the initial voltage was 30. So that way it loses 10 in the beginning, then 10 more, and then another 10. So in total it lost all of the voltage that it started with, which is in accordance with Kirchhoff's voltage law. So in other words, the mistake here was that the source should have measured 30 volts. For C, for a circuit with two lamps connected in parallel, a student measures the voltage drop across one lamp to be 20 volts. The student measures the voltage drop across the second lamp to be 10 volts. So here we have lamps that are connected in parallel. Okay, so we have lamps connected in parallel. A student measures the voltage drop across one of them to be 20 volts. and the student measured the voltage drop across the second lamp to be 10 volts. Now this is a violation of Kirchhoff's voltage law. So whenever you have loads connected in parallel, given that there's only one on each of the two different paths, the voltage drop has to be equal. So in this case, you can have 20 volts on one side and 10 on the other. So you either need to have this to be 20, or the other possibility is that the other one has to be 10. So there are two possibilities here. So here, let me try to show you that in a better way. Give me a second. So again, in parallel, the voltage drop has to be the same. So if it's 20 volts in one, it has to be 20 volts in the other. Or if the first one was 10, then this one also has to be 10. So there's two possibilities here. So in both of these, we can say that the student has made a mistake in doing their measurements. So we have two possibilities. So both of them are due to Kirchhoff's voltage law, KVL. Alright, and then for part D, we have a student is using an ammeter and notes that it reads 0.15 amps on the first lamp and 0.2 amps on the second lamp and 0.25 on the third lamp. The student says the lamps are connected in series. So again, we have 3 lamps connected in series, but somehow the current is increasing, and this is already a direct violation, because in a series circuit the current should remain the same. So this is a very big mistake from the student. So the current should not decrease when it's connected in series. So there has to be a big measurement problem here. There's no real way to correct this. So the violation that we have in this case is Kirchhoff's current law. For question number 2, we have, for each of the following circuits, the given values are listed in a table. Copy each table into your notebook and find the missing values. Alright, so here we're going to be using Kirchhoff's current law and Kirchhoff's voltage law. And let's look at what we're trying to find. So let's try to see the convention of current is moving along. So this is I source, the current from the source. And the first thing that it encounters is the lamp 1, which is I1, the current at the first voltage drop. So these two are connected in series. So we suspect that the current at the source will be equal to the current at the first lamp. And if you look at the table, they give you the value of the current at the lamp 1. So this would be the current of the source, 3 amps. And as the current continues to travel, it meets a junction, so the current is going to split. And this means that the current of I1, because it splits, it should be equal to the sum of the current that went to lamp 2 plus the current that went to lamp 3. And if we look at our table, we have I1, we have I2, and we're looking for I3, so we can just isolate this. So 3 minus 1.5. So the current at the lamp 3 is going to be 1.5 amps. So that takes care of the current. Now let's look at the voltage drop. So remember, the voltage drop from the source has to be lost in each of the following close paths. So this means that the voltage at the source has to be equal to the voltage at the first lamp plus the voltage at the second lamp. And if we look at this, we're given the values of V1 and V2. So the voltage at the source has to be 3 volts. And by the same reasoning, we see that there's another loop. So the first loop, and then we have another outside loop. So V source will be equal to V1 plus V3. And once again, V3 will be the V source minus V1. So that would be 3 minus 2, which would be 1. Now that was one way of thinking about it. You have the complete loops, or you could have always just referred to the two lamps 2 and lamp 3 connected in parallel. So that means that the voltage drop should be the same. So these two should both be 1, which it is in this case. So that's our table for the first part. Now we do have other examples, so let's take a look at part B. And it's usually good to start with the current, but again, you could do either way first. So I like to look at current first. So the current at the source is going to start traveling, so that direction of enconventional current will be traveling along the positive terminal, and it's first going to encounter lamp 1, but because these two are connected in series, the current at the source is going to be equal to the current at I1. So if you look at a table, we're given the current at the source, so this is the same as the current of the lamp 1. Which would be 2 amps. And then once it meets the junction, our current value is going to split, and it splits such that the sum of the current going to 2 plus the current going to 3 is going to be the current that was entering the junction. So here we have the value of I2 was given us as 1, I3 we don't have, but I1 we have as 2. So solving for current 3, it's going to be 2 minus 1, which would just be 1. And once these two meet back at the other end of the junction, they should get back what was going in. Remember, the current going into a junction equals to the current out of the junction. So that should be back to what I1 was. And since I1 is connected in series to I4, those two will actually be the same. So I1 is actually equal to I4. So that would be 2 amps. Now here's the same question, but now I'm just going to have it clear so you could just focus on the voltage. And for the voltage, remember, all the voltage that you have at the source has to be lost in a complete circuit. So here we have the voltage at the source. Has to be equal to the voltage dropped at 1 plus 2 plus 4. Right, because that's a first closed loop. And then by the same reasoning, we could have done it for the bigger loop, or we could do another reasoning that these two are connected in parallel, V2 and V3, so those should actually be equal to one another. V2 should be equal to V3. And if we look at our table, we're actually given V2. V2 is 6 volts, which is what V3 will be. So we could fill in the table. And now we can fill in the V4 by looking at our expression and isolating for V4. So that would be 8 volts, right? Because all the voltage at the source, which is 24, has to be lost along the path of V1, V2, and V4. So we added those together, but we isolated for V4, which gave us 8 volts. So filling in from the previous one, this should be in 6, and this should have been 8. Alright, so I think this is the last example for this homework. So let's try to see if it gets more complicated. Maybe you're feeling more confident by now. So here they want us to fill in the table, and once again, first I like to look at the current. So the current at the source, and is the conventional current, so it's going from the positive terminal, and it first encounters the voltage drop at lamp 1, but since these two are connected in series, they should be equal to one another. And if we look at our table, we're actually given the current at the source, which was 4 amps. And that would be the same thing as the current at lamp 1. Then once again, our current 1 enters a junction, so it's going to be split into the 2 parts. So our current at 1 is going to be split along the current at 2 plus the current at 4. Notice here I didn't put I2 plus I3 because notice that lamp 2 and lamp 3 are connected in series, so the current in that branch should be the same. So right away, because the lamp 2 and lamp 3 are connected in series, the currents should be the same. So if we look at our table, I2 was 2, I3 we don't have, but it's actually equal to one another, so we can do this part first. This will be 2 amps. Then we look at our equation to find the current at lamp 4. So we just bring the I2 to the other side. Which would be 2 amps. And now if instead we focus on the voltage, remember all the voltage at the source has to be lost in the circuit. So the voltage at the source is going to equal to V1 plus V2 plus V3 if we consider one path. We could consider the other path where V source will be the sum of V1 plus V4. Or yet another strategy, because lamps 2 and 3 are connected in parallel to lamp 4, this means the lamp V2 plus V3 should be equal to V4. So we have 3 equations to work with, all according to Kirchhoff's voltage law. So let's see which ones we're going to be using to fill in our table. So we have the source is 6. So from these 3 equations, now we can work with them to find the missing parts. So notice that we were getting the voltage at lamp 2 and lamp 3. So we could use this part of the equation. We have the voltage at 2, which is 1, and the voltage at 3 is 2. So V4 should be equal to 3 volts. And then we have that the voltage at the source which was 6, equals to V1 plus V4, which we now found to be 3. So 6 minus 3 will be V1, so 3 volts. But we could even use the other equation if we want to, right? Because here we have 6, V1 we don't know, V2 they were given to us as 1, and V3 was given to us as 2. So I'm just showing you a different way. But you see, we still get the same answer. So we're very likely to be correct. And that takes us with our first introduction to circuits, and we're going to be looking at more complicated circuit analysis. So make sure that you stay tuned and watch the other videos.